Günaydın. The title of my talk today is Konuşma Tanıma, Gerçeğe Kaldı. For those of you who don't understand Turkish, this is speech recognition, what's left? It's in the lapel? Okay, great. And I wanted to thank all of you for inviting me here today and for all your kind hospitality. So I first want to start with the inspirations for this talk. And the inspirations are my two thesis advisors at MIT. Nat Durlak on the left, who died last year, and Lou Breda on the right from a 1993 picture. Both of them were honored at the Acoustical Society of America in Boston last June with two special sessions. They made fundamental contributions in psychoacoustics and sensory communication aids. They taught me how to scientifically assess aspects of human perception, and I learned how to do research from them, to be thorough and how to question. And as all of you start your graduate careers or work through your graduate careers, I can't stress enough how important it is to find a good mentor to shepherd you through graduate school and through whatever research work you do. Now, before I get into the main body of the talk, I'm from IBM, and I wanted to mention say a few words about IBM. We have a long history of innovations in artificial intelligence, ranging from the first working chess program back in 1957, all the way through, more recently, the first computer to defeat the best human Jeopardy players, our Watson system. Some of the AI challenges we're tackling today at IBM Research AI, artificial intelligence, include projects in the media area, such as creating highlights of sports events automatically, in the customer care area, creating a bot that can guide a user through buying the right insurance policy, and also in the healthcare area to try and improve the accuracy of breast cancer screening. I'd be very interested in talking to you more about other projects that are going on at IBM. I also urge you to visit the IBM Watson Playground that my local colleagues have set up downstairs, and also enjoy the Watson bag and IBM notebook that has been left on your seats today. Okay, so let's get started here. This is a chart of historical performance in speech recognition. The task itself is transcription of something called switchboard, a set of human-human landline telephone conversations on a set of directed topics. What that means, by directed topics, I mean the two people were put in two different rooms, given two ends of a telephone, and told to talk about a particular subject. Be that sports, be that buying a car, being that education, and told to have a 5-minute to 10-minute conversation. The calls were then transcribed. Switchboard itself is a popular public benchmark in the speech recognition community. It's difficult enough to present challenges, but clearly understandable by humans. And over the years, when we first started working in Switchboard, our performance was terrible. We were getting about 80% of the words wrong back in the early 90s. Today, we're down to about 5% of the words wrong, with most of the gains, a lot of the gains occurring just over the last few years because of the impact of deep learning. Now, one question you may ask is, everybody understands speech. Why has this been such a difficult problem to tackle? And there are many different reasons for this. First of all, there's a lot of variations between speakers. There are a lot of variations between the channel in which you communicate speech, be it a wide bandwidth microphone or a telephone or a far field microphone. There could be background noise. People could be speaking with different accents. So this is a picture from the movie Gone with the Wind, which took place in the Deep South in the United States, where people have pronounced accents. And this is some guy from New York who may look familiar to you over here. Another reason is because people use different speaking styles. When they speak, they may stutter when they speak. They may speak very clearly. But probably the biggest reason that speech recognition is difficult is that there is a huge acoustic variability even when you say the same underlying text multiple times. So these are three different utterances of the phrase, the girl with the dragon tattoo. And for those of you who are unfamiliar with this representation, this is something called a speech spectrogram. The horizontal axis is time, the vertical axis is frequency. The frequency range goes from about 200 hertz to 8 kilohertz, and these dark horizontal striations correspond to the resonances of the vocal tract that shift around when you move your articulators, when you move your teeth, when you move your tongue. And to just highlight one aspect of these pictures that change, just look at the ooh, being difficult here. Just look at the ooh in the word tattoo. And you could see that three different versions of the word ooh look significantly different from each other in the position of the resonances of the vocal tract. So this inherent variability of speech is the biggest challenge we have to face with in producing high accuracy speech recognition transcription systems. So what I'm going to do now is take you on a brief tour of the very basics of speech recognition systems. And the basic formulation of speech recognition that has been around since the early 70s is as follows. What we do is we imagine we observe some set of acoustic features extracted from the speech signal we'll call X. And our goal is to find the string of words W that has the maximum a posteriori probability of occurring given you observe a set of features X. We can rewrite this as P of X given W times P with a little probability trick times P of W over P of X. Maximizing this term on the left is not a function of the term on the bottom. So it basically boils down to finding the word string W that maximizes the product of these two terms over here. And this therefore defines the entire speech recognition problem, because you have to decide what the vocabulary is, you have to decide what the features you're extracting from the speech signal are, you need a model that predicts the way the speech features X are produced from an individual word or string of words. This is what we call an acoustic model. And then you need a model for predicting the probability of word strings. This is what we call a language model. Last of all, you need an efficient way of searching through all the many possible strings of words to maximize this quantity. That's called the hypothesis search. It's a little easier to see what's going on if we use a block diagram of the main components in a speech recognition system. So what we do is we take a set of features from the speech signal and we put it through what we call a speech recognition decoder. The speech recognition decoder is another word for the hypothesis search. And the decoder itself takes as input not only the output of the feature extraction process, but also the acoustic model and the language model. It combines these three sources of knowledge together and outputs a transcript. Optionally, there may be, an adaptation phase at the bottom that's fed back into the acoustic model and sometimes the language model to improve the estimates of the acoustic model based on what was recognized to generate further improvements in overall performance. So what I'm going to do now is to walk you briefly through these different components from a historical perspective. First of all, how do we choose a vocabulary for a speech recognition system? And the way we do this is very simple. We take a lot of text, we count the number of words, and we take the most frequently occurring words. If we want to do something fancier, we can also look at the intersection of frequently occurring words in diverse sources of information. So for example, we can look at frequently occurring words in news stories versus conversations and look at the intersection of the frequently occurring words. Another thing we need to do is we need to create something called a lexicon. A lexicon is a mapping from the word spellings in the system to the underlying pronunciations. And let me point out that particularly in English, this is not a trivial thing to do. So for example, the word that is spelled in English Tomato can be pronounced either as tomato or tomato. The pronunciation, particularly in English, is very hard to predict from the spelling. Orthography is a fancy name for spelling. And just to give you an example, I'm sure many of you have seen in your early English studies, if you see the word spelling T-H-R-O-U-G-H, you might think it's pronounced thrug rather than through. Okay? In addition, the text you're analyzing to find frequently occurring words may have misspellings in the text. There are also many language-dependent problems in selecting a vocabulary, or a lexicon. So for example, Arabic is a language written without vowels. Chinese is a language written without white spaces between the words, so you don't know where the words begin and end. Another point to make is the recognizer itself cannot produce words outside its vocabulary. So depending upon the task, vocabulary sizes from 5,000 words to 500,000 words are common. But just to point out, the computation in the system does not grow linearly because many words share part of other words. So for example, the word house is the prefix for the word houseboat. And you could take advantage of that to cut down on the amount of computation you actually have to do. And I'll say a few more words about that in a minute. So, next thing I want to talk about is what's the nature of the features we use in the system. And what we do in terms of features is we extract a set of time frequency features that are related to the processing that goes on in the human auditory system. To a very crude approximation, the human auditory system does a filter bank analysis on the input speech where the filters are spaced linearly below about 1 kilohertz and then logarithmically above 1 kilohertz. So above 1 kilohertz, the filters get wider and wider and wider in bandwidth. Okay? Now, what we do, and a picture of such a representation is shown over here. Now, what you can see in this picture is that you see a lot of correlations between the outputs of the filters in both time and frequency. So what's often done is to decorrelate the features to allow for easier modeling. This is done by taking something called a by extracting something called cepstral coefficients. You can just view this as an orthogonalizing transformation on the input features. In addition, the features themselves are usually augmented with their time derivatives. So the basic features in the speech signal are the cepstral coefficients augmented with the time derivatives, and they're extracted 100 times a second. The next thing I want to talk about is how we build an acoustic model. And the way we build an acoustic model in most standard speech recognition systems today is we use something called a hidden Markov model. A hidden Markov model can be thought of as a finite state machine with a bunch of transitions. And every time you take a transition, you output one of the feature vectors in the system with a certain probability. So when you go from this state to this state, you output a feature vector. When you just stay in the same state, every time you take this transition, you produce a feature vector. And different sounds are associated with different probability distributions of the feature vectors. The typical modeling representation we use to represent the probability distributions are mixtures of Gaussians, because if we just, a simple Gaussian distribution is just too simple to capture the shape of the distribution. So we typically use mixtures of Gaussians down here. And in addition, the probability distributions on the individual states are different to capture the microstructure of the underlying speech sounds. Now, once we have our basic hidden Markov models for the individual speech sounds, which we call phones, the next question is how do we build up models for words and sentences? The way we do that is we have an inventory of models for the speech sounds, and then we take our lexicon, where we represent each word in the dictionary as a simple directed graph, and we just plug in the models for the individual speech sounds, creating a much more complicated graph that looks something like this. But the way this is done is just by taking these models and embedding it into the overall graph for the sentence. Other fine points about the acoustic models: we actually build models for different sounds in different contexts, because the way in which you say a P depends on whether the next sound is an A or an E. If you ignore that, you don't get as good recognition performance as if you pay attention to that. There are efficient algorithms that exist to train the models from a set of transcripts and data. Don't have time to go into that today. There are push-button toolkits exist that enable easy creation of such models. And additional enhancements include training algorithms targeted at improving the discrimination power across words and phones, rather than just increasing the likelihood of the training data. Okay? Next thing I want to talk about is the basics of language modeling. How do we compute the probability of a word string? So we could write the probability of a word string W1, W2, et cetera, as the product of the probability of W1 times the probability of W2 given W1 times the probability of W3 given 1 and 2, et cetera, et cetera, et cetera. So the probability of the word string is just the product of these individual terms. We then make what's called the Markov assumption, which is that the identity of the next word depends only on the last n-1 words. Let's say n equals 3. In that case, we can represent the probability of the current word not as conditioned on the probability of the words in the entire sentence, but just on the 2 previous words in the sentence. We then count the number of times a word occurs after a series of n words. Each separate context is called an n-gram. The models themselves are typically built from millions or even billions of words of text. A small language model may have 4 million n-grams in it. A larger language model may have 30 million n-grams in it. And it's interesting to point out that a single acoustic model often suffices, is often adequate for a large variety of applications, but different language models are needed for different situations. So often the work in moving from one task to another is building a new language model and leaving the acoustic model alone. Okay? I now want to give you a very brief idea of how the hypothesis search in the system works. And let's imagine we have a very simple 9-word vocabulary, where the first word can be Jim, Jill, or Bill, and the second word could be read, wrote, or fled. What we then do is we make a giant directed graph of all the word sequence possibilities in the system, like this. And then we take this graph, and we'll only focus on the beginning part of the graph here, and we plug in the phonetic representation for the individual words in the sentence. Okay? So you could see in this picture, you could see that the word Jim is represented by a J sound, an I sound, and an M sound. Jill is by a J, an I, and an L. And Bill is represented by a B, an I, and an L. Now, you could see that this can quickly get out of hand if you have a different path through for every word in the vocabulary, particularly in today's recognition systems where there are 500,000 words or more active at a given time. However, as I mentioned earlier, you can simplify the graph by taking advantage of the fact that many words share the beginnings and ends with many other words. And what you can do then is reduce that somewhat more complicated graph into a much simpler graph that looks like this. So you still see the three different words in the system. The top path just represents Bill, and then the bottom graph represents either Jill or Jim. So what you do is you take all the knowledge sources in one large graph, the acoustic model and the language model, and then you simplify this using a process called minimization and determinization. Again, don't have time to get into that today in this talk. There are efficient algorithms exist to search the graph. Some systems make multiple passes over the data with progressively more sophisticated models to reduce the overall computation. And performance improvements can also result by combining results of multiple systems together. Okay? So in the last part of the introduction, the last question you can ask is, how do we know we're doing well? Okay? And the obvious success metric in speech recognition, which is actually one of the most beautiful things about the speech recognition problem, there's a very simple performance measure that's been used for years and years and years, is the word error rate. And that's just defined as 100 times the number of substitution errors, plus the number of deletion errors, plus the number of insertion errors, divided by the total number of words in the reference transcripts. So to work through a simple example, the reference here is the cat in the hat. And let's say the recognizer outputted cat is on the green hat. So what do we see? The word the is deleted, that's a deletion error. The word in is misrecognized as is, that's a substitution error. The word on is inserted, and the word green is inserted. So we add up the substitution, deletion, and insertion errors, divide by the total of number of words in the reference transcript, which is up here, multiply by 100, and get a number here of 80%. And this word error rate is something we've been optimizing since time immemorial. And again, the simplicity of this is one of the nice things about speech recognition. Unlike many other areas you run into, particularly in the artificial intelligence space, this is a very simple criteria, simple to understand, simple to convey, and it's not prone to a lot of, you can't make up a lot of stories about this. Either the word error rate gets better, it stays the same, or it gets worse, okay? You can't dance around these things, which is, in my opinion, being a simple person, good. Okay. So, let's now talk a little bit about neural networks. So if you remember from the first slide I showed you that sort of went down from 80% down to 5%, some of the biggest advances in speech recognition have taken place over the last few years, and they've primarily been driven by the advent, the popularity of neural networks. So to just review what I was saying before, the acoustic model in a speech recognition system allows us to predict the P of x given W, the probability that a word produces a sequence of observed feature vectors. A word is modeled as a sequence of phones using a set of 3-state hidden Markov models as shown in the bottom of the slide here. Each HMM state corresponds to a context-dependent subphone unit we will call C sub I. And traditionally, the output distribution in each state has been modeled by a Gaussian mixture model, otherwise called a GMM, trained to maximize the likelihood of the data or its discriminability. Neural networks can also be used for acoustic modeling instead of GMMs because all a neural network is a function approximator. In spite of hearing a lot of fancy things about their intelligence, they basically do function approximation in the same way a Gaussian mixture model does function approximation. Neural networks were originally tried in the early 1990s, but until the onset of deep learning, could not be made to perform as well as the Gaussian mixture models. So now let's talk a little bit about how neural networks are applied to the speech recognition problem, okay? So in its simplest form, we'll first talk about a multi-layer neural network. It's also called a feed-forward network or a deep neural network, a DNN, and that's how I'll be referring to it in the rest of the talk. So the neurons themselves are arranged in a sequence of layers. Each neuron in this simplified neural net consists of a series of weights followed by a nonlinearity, a set of weights and a nonlinearity. The outputs of the individual layers are called activations, labeled with A, and at the very top of the network, what we're doing is we're predicting the subword class C sub I. And the way this is done is that the activations at the highest layer are then put through an exponential nonlinearity and divided by the total sum of all the exponentiated activations so that the whole set of P's are guaranteed to always add up to 1 and none of them are negative. And that allows us to basically use this as a set of likelihoods in a speech recognition system, as I'll show you in a second. So the problem is the setup is fine. The big issue is where do we get these weights from in the system? And we get the weights by training something called the cross-entropy objective function. And the cross-entropy objective function is given as the sum over all the different frames in your training data and as the product of two terms. This one here called y and this one called log p. Now, log p of c sub I given x of t is just the posterior probability that the subphone c sub I occurred at time t. So it's just the output of the neural network. Y sub t reference is the target vector at time t. And what this is a one-hot vector indicating the occurrences of the subphones over time. So let's imagine we're dealing with the word cats, and it has 4 subphones, and the first one occurs at time 1, the second one at time 2, the third one at time 3, and the fourth one at time 4. And since A does not occur at time 1, we put a 0 here, et cetera, for all the other positions in the reference vector. The neural network, of course, is producing a much smoother version of these ideal target probabilities. In a perfect world, the output of the neural network would line up exactly with the y vectors, but since the approximations, the predictions are imperfect, it doesn't, and you see smoother numbers that look like this. So you just take these output vectors at each time, multiply it by these vectors, take the logarithm of these things, multiply it by these vectors, add the thing up, get a number. Okay? And then what you do is you take the gradient of that number, of that objective function, with the respect to the parameters in the system, and then you update that iteratively over time using an algorithm called stochastic gradient descent that I hope you heard a little bit about yesterday from my colleague Murat. Another thing you have to do is that the neural network itself is only giving posterior probabilities, so we divide by the class prior in order to get something that's proportional to an actual likelihood. And this neural network likelihood can then replace the Gaussian mixture likelihood as an output distribution in the hidden Markov model. And this formulation is called a hybrid neural network acoustic model, and it's one of the most popular acoustic models being used in the community today. Okay? Couple of factors affecting neural network performance. On the left, you see that as you increase the number of subphone units and make them more and more finer grained, the word error rate drops. Similarly, as you add more layers in the neural network, the word error rate drops as well. Now, the next thing I want to talk about are two enhancements to the basic DNN formulation that we came up with at IBM. One of these things is called sequence training, and it deals with the following issue. The cross-entropy frame-based objective function ignores the fact that we're really interested in word-sentence discrimination, not frame discrimination. So the idea is to switch to a sequence criterion as an objective function. So what do we mean by a sequence criterion? I'll say that in a second. And what we're going to focus on is basically the gradient to simplify the discussion, we'll focus on the gradient update term in the system. So for the cross-entropy function, the gradient update that you use to update the weights in the system is composed of two terms: the difference between the a posterior frame-based probability and the reference at a particular point in time. In the sequence criteria, instead of conditioning the output unit on just the input frame at time t, you condition it on the entire sentence. So you take advantage of the knowledge of the entire sentence in order to compute the posterior probability of that output unit. Corresponding to the reference is you do the same thing. You take the probability of the output unit, you condition it on all the feature vectors in the sentence, and also the correct word transcription for the sentence. So that gives you a term akin to the reference term in the term above here. And the reason it's called a sequence criteria is you're conditioning the probabilities on the entire sequence of input frames, not just one input frame in the sentence. Another enhancement we made in the system is something called a convolutional neural net, which was inspired by work in the image processing area. So down here we have a spectrographic representation of the signal. Again, we have time on the horizontal axis and frequency on the vertical axis. And again, you clearly see that speech is locally correlated in time and frequency. And the idea in a convolutional neural net is to try and construct a network that's specifically designed to capture these sorts of local correlations. And let's show you how this works by means of a little cartoon, what's called a speech cartoon. So here, what we have is the weight matrix in the system, W. And here, this is a cartoon of the spectrographic representation of the system. So the bottom horizontal rows, again, correspond to time, and the vertical rows, the columns correspond to time, and the vertical row, the rows themselves correspond to frequency. So what we do in a standard DNN configuration is we take the weight matrix, we multiply it by a slab of the spectral representation, and we produce a set of outputs. Then what we do is we take the entire weight matrix, slide the whole thing to the right, multiply it again, produce another set of outputs, et cetera, and work our way through the entire spectral representation of the system. Now, in order to capture local correlations in the speech signal, we do the following. We use a much smaller weight matrix. This is still our spectral representation over here. And what we do is we take this weight matrix and we multiply it by the bottom part of the spectrogram. We produce a set of outputs, then we shift it up one row, one frequency position, and produce another set of outputs. Then we shift it up another position and produce another set of outputs. Then we proceed and we redo the whole thing all over again. And by having a much smaller window, a much smaller weight matrix that's focusing on a much smaller fraction of the spectrogram, it makes it much easier for the system to learn local correlations in the signal rather than having to deduce it from some large weight matrix that weights all the components of the system and is much harder to learn without outrageous amounts of data. Okay, so where are we? What good does all this do us? Okay, so let me just say, here are just some word error rates that result from these various techniques. So let's take a system that's been trained on 300 hours of training data and a basic Gaussian mixture model. Word error rate is about 14.5%. When we build a DNN off of this, we get down to 14.1%. But if we build a CNN off of it, we get down to 13.2%. Similarly, if we take our DNN system and we apply the sequence training criteria to that, the error rate moves from 14.1 to 12.5. And for the CNN, similarly, the word error rate moves from 13.2 to 11.8. Now, another way you could improve the performance of a speech recognition system is what you can do is you can add more data to the system. So this column over here is now a system trained on 2,000 hours of training data. And you could see that the cross-entropy performance for the CNN goes down to 12.6, but the sequence training goes down to 10.4, which is actually considerably larger than it goes down to from 13.2 to 12.6. And what this sort of shows you is that certain techniques in training any sort of machine learning system, some are better at utilizing lots of data than others are. And here the sequence training criteria is able to better make use of the extra data than the cross-entropy function is. And this number 10.4, I want you to remember that because we will be returning to that in a few minutes. Okay? Now, let's get in. A lot of this stuff was done about 4 or 5 years ago. Maybe it's 5. Yeah, 4 or 5 years ago is about right. Let's now start talking about some more recent enhancements in speech recognition. So one technique is something, again, we did at IBM. It's something called an unfolded recurrent neural network. And the thing to point out is that a feed-forward neural network has no memory over time. The time course of behavior of a speech sound is typically captured with an HMM, but the behavior that's captured in a feed-forward neural net is all very local. So a neural network for time-varying behavior is something called a recurrent neural net. And here's the basic formulation. The output layer is computed the same way as in a normal neural network. Y sub t is the output. It's just the a posteriori probability of the output subphone given the input feature vector, which is computed with a softmax function multiplying a weight matrix times the output activations, which we're calling h of t. The activations, though, were computed a little differently. In a basic DNN system, the output is computed by taking the weight matrix times the input features and passing it through a nonlinearity. In a recurrent neural net, we add a second term. The second term is a weight matrix times the activations at the previous time frame, t minus 1. And we then iterate through this process from 1 to t for the total number of input vectors. Now, for a simple RNN architecture as described above, it's possible to perform frame unrolling. And the way frame unrolling works is as follows. What you do is you take the basic formula for the activations at time t, which is just the nonlinearity times the weight matrix times x sub t plus the other matrix times h of t minus 1. Then what you do is you plug in the formula for h of t minus 1 into here, and you replace it with sigma, the nonlinearity, times the weight matrix times the feature vector at t minus 1 plus the weight matrix times the feature vector times the activations at t minus 2. And you iterate this over and over again, typically about 10 times or so. This effectively turns the recursive network into a feed-forward network. And what this allows you to do is it allows you to get some of the benefits of recursion, but by letting you allows you to continue to leverage your pre-existing training infrastructure for training the neural network, which is also a good thing. Now, the problem with these simple recurrent neural networks is that the gradients themselves decay exponentially in time. And that makes it somewhat harder to capture long-term dependencies. There is a much fancier sort of recurrent neural network called an LSTM, otherwise called a long short-term memory network, that adds a set of tradable gates that allows information to be stored for longer periods of time. And today, in the best acoustic models, the systems employ bidirectional LSTMs, where you take predictions both going from left to right in the network and also from right to left, and combining these predictions together. And then what you do is you stack multiple LSTMs up on top of each other, typically to about 4 to 5 layers. Now, another enhancement is in the convolutional domain, and this is something called a VGG network. In a basic convolutional network, which is shown on the left, you have a couple of convolutional layers, and at the top, a bunch of completely fully connected layers, like in a DNN. In a VGG network, you have a lot more convolutional layers, consisting of lots and lots of tiny convolutions that you sort of build up as you move higher and higher up in the network. And at the top, you still have a bunch of fully connected layers. Now, another set of enhancements we've employed to get better results. All the previous results I was describing was using what we call a 4-gram language model with 4 million n-grams and a vocabulary of 30,000 words. One of the enhancements we've made is to combine 3 different language models together with an overall vocabulary of 85,000 words. We're using a bigger n-gram language model, moving from 4 million n-grams to 36 million. We use a feed-forward neural network-based language model. Unfortunately, I don't have time to go into that today, but some of the talks later in today, you may hear may describe some of these things in more detail. And then we also use something called a class-based language model. The idea in a class-based language model is instead of conditioning the current word, the probability of the current word on the previous 2 words in the system, you also condition it on the class of the previous words in the system. And what this, where a class could be, you know, animals, days of the week, et cetera, et cetera. And what this does is it adds some smoothing to the language model that aids the overall robustness of the system. Most very recently in speech recognition, these are just 2 things we came up with last year that we've applied to the speech recognition problem, are something called adversarial networks and something called convolutional inspired neural network language models, or we also refer to it as a WaveNet language model. The basic idea in this adversarial model over here is that the objective function consists of 2 terms. Term number 1 on the left is just the a posteriori probability of the subword units. The one on the right is the ability of the network to separate different speakers from each other. And what you may imagine you want to do in a neural network is you don't want to have the network wasting a lot of time separating speakers from each other. You want it to focus on separating sounds from each other. So what you do is you take the output of the network on the right, and rather than adding it to the output of the network on the left, to the objective function on the left, you subtract it. And this encourages the network to not waste its time on separating speakers and to focus more on separating sounds. In the neural network, a convolutional neural network language model, basically we use the same ideas in convolution we applied to speech recognition and apply it to actually constructing a neural net language model. Now, the last set of things that I just want to mention briefly to give you some very rough idea in terms of what research is going on today in speech recognition is something called direct acoustics to word automatic speech recognition. And what we do in a direct acoustics to word model is we eliminate all modeling assumptions in the system and rely totally on deep learning. In particular, what we do, in our standard system on the left, we have a fairly complex architecture consisting of an acoustic model, a language model, a hypothesis search, and the system is not a simple system to program, implement, particularly from a deployment point of view. In a speech-to-word model, you just read the words right out of the network directly. There's one network that rules everything. And it doesn't use a dictionary, it doesn't use an explicit language model, and there's no speech recognition, hypothesis search, or decoder. So this is a true end-to-end model. Now, at this point in time, at least in our experiments, the performance of these systems are good, but they're not as good as the hybrid models. But they're certainly getting better and better all the time. And if you go to a speech conference, you'll see a lot of attention being paid to models like this. But as of today, as far as I can tell, the hybrid models, at least for the tasks we run against, are still the best models. OK, so what does all this do for us? Remember this number 10.4. That was where we were with just sequence training and the application of convolutional neural networks. When we add a recurrent neural net, an unfolded recurrent neural net, we take 10.4, knock it down to 9.9. The VGG model takes 10.4 and knocks it down to 9.4. When we combine an RNN, a VGG, and an LSTM, we knock the word error rate down to 8.6. And we add more n-grams in the class-based Model M language model, we knock things down to 7.0. When we add in the feed-forward language model, it goes down to 6.6. Next thing you do is compare line 7 and line 5. When we switch in adversarial learning and a fancier form of VGG model called a ResNet, the acoustic model performance goes from 7.0 down to 6.7. And when we add in a bunch of additional language models based on LSTMs and this convolutional language model, the word error rate goes down to 5.5, which is a pretty good number. So another question you can answer is, what is human performance on this task? And we attempted to answer that by actually measuring this. We took a bunch of skilled transcribers, gave them the switchboard test set, and asked them to transcribe the switchboard test set and compared their transcriptions against the gold standard reference that had been worked on for years in the community. And the best transcriber got an error rate of about 5.1%. Compare that to the machine performance of 5.5%. Okay? So, does this mean we're now done with speech recognition because we're both getting comparable results to human performance? Can IBM finally stop paying me to work on this problem? Well, there are a number of caveats in the experiments I've been describing. The results themselves have been strongly tailored to this individual corpus. We trained on 2,000 hours of strongly targeted data, both for the language model and the acoustic model. The data itself is relatively high quality, even though telephony-based speech. It's relatively accent-free. And the nature of the conversations, because people were told what it was they were supposed to be talking about, is somewhat artificial in nature. It's not completely fluent speech. So what happens when speech systems have to deal with variations in accent, noise, speaking style, and domain switching? So what we did was we took that wonderful 5.5% word error rate system and we threw different data at it. So, and we're pegging the base performance of the system down at 1.0. So when we throw broadcast news at this stuff instead of conversations, the word error rate goes up by 40%. When we throw real conversations at the system, the word error rate doubles. When we throw emotional speech at this system, the word error rate triples. When we throw noisy speech at the system, the word error rate triples, and also for accented speech as well. Now, we know that task-specific data would help a lot. If I collected 2,000 hours of accented speech, and built a system off of that, clearly the word error rates would be much better than I'm reporting here. But do we really have to put in this level of effort for each language we build in each domain? And the other question, inspired by our work on measuring human performance in Switchboard, is what are human abilities in terms of our being able to cope with these variations? So in the last part of the talk, I want to look at the following areas: noise, speaking style, accent, domain robustness, and language learning capabilities, review the state of the art of human and machine performance in these areas with a goal to try and make the case that we still have a long way to go in speech recognition, so let's keep doing research in this area. Okay, let's start with human performance of noisy speech. This is something that has been studied for years and years and years. And I'm actually using in this talk a study that was done back in 1951, which, believe it or not, is actually even before I was born. What we see here on the bottom is signal-to-noise ratio, which is the logarithm of the ratio of the speech energy in the signal to the noise energy. So 0 means the speech and the noise are roughly about the same amplitude. And the vertical axis is intelligibility, which you could sort of think of as a human word accuracy, or 100 minus the word error rate on the left side. And this study shows, no surprise, that the intelligibility of speech depends on the predictability of the materials. The more predictable, the better the performance is as the noise level increases. And for words and sentences, which is what we're interested in here today, for humans, you start seeing a degradation in performance about 10 dB or so signal-to-noise ratio, and it goes down to about 0 dB by around minus 7 dB signal-to-noise ratio. How do speech recognition systems perform? Well, this is an old graph, but still is meaningful. Back from 1996, on a 5,000-word vocabulary task, comparing a bunch of signal processing schemes designed to enhance speech, designed to enhance the speech signal. And what you can see here is with the simplest schemes on the right, they're not very effective in achieving robustness. The error rate the accuracy starts declining around 20 dB and is effectively 0 by about 7 or 8 dB. The better signal processing systems, for example, that dark line on the left, starts falling off about 10 dB, but is pretty close to chance by around, I don't know, by around 0 dB or so. However, there's one trick you can apply to achieve a lot of robustness in noise processing. It's something called multi-style training. And what you do in multi-style training is you take clean speech and you add in all sorts of representative noise and build one big model off of all these combined sources. You train it all up, and lo and behold, the degradation in the system begins to look a lot more like human performance than being very non-robust. Now, today, with the, just to parenthetically make a comment, the interesting thing about neural networks is people who work in this area seem to be rediscovering things we in the speech community have known for many, many years. So today, they now call what we're calling multi-style training. The fancy neural network term for this is data augmentation, okay? Be it known, we came up with this first in the speech community, okay? Data augmentation is just a rehash of multi-style training. Okay, now that was an old story, an old study. More recently, you can ask, how does deep learning affect speech recognition, performance, and noise? Well, it tends to improve performance across the board, but no special advantage is seen for noisy or reverberant speech using deep learning. It's not, a magic bullet for noise immunity. There have been a bunch of recent challenges in the speech community. By a challenge, I mean something where people throw out some speech data, and they challenge the community to do well on it. And what they found is that in these various challenges, you achieve the best results by combining a variety of techniques: multi-microphone processing, multi-style training, combining multiple systems together. And when you do all of these things, you could basically take a system that falls apart in noise up here and gets very close to the performance of speech in quiet, which is that red line. The lowest systems, like that narrow purple line right above the red line, is what you can achieve when you throw a lot of different techniques for noise immunity at the system. So you could do pretty well on noise immunity if you throw a lot of firepower at the problem. Okay, what's another thing that affects speech intelligibility? Well, another thing that affects speech recognition performance, and we'll first start by human performance, which is speech intelligibility, okay? This work came out of work I actually did in my doctoral thesis, where the goal was to try and build signal processing systems for people with hearing impairments. And the idea here was to try and mimic what people do when they speak clearly, when they speak to a hearing impaired person. And one of the things you can ask is, maybe when you try and speak clear, in an exaggerated form of voice, you actually don't make yourself more intelligible. You actually distort the signal. So you can't take these things on faith. You actually have to measure it. And lo and behold, what we found in one of our early studies is that the intelligibility of speech when spoken informally, which we're calling conversational, versus more formally or clearly, goes up significantly for hearing impaired listeners. And what we then did was we studied the acoustic things that were changing in the speech signal to get some handle on what people actually did when they speak clearly. So one obvious thing people do is they speak more slowly. These are speaking rates in words per minute for conversational versus clear speech. And in some cases, the speaking rates almost are reduced by a factor of 2. Another thing you do is you don't modify the basic characteristics of the individual speech sounds. So for example, in clear speech, you say each vowel very clearly. It's well formed. In conversational speech, you make a lot of modifications to the basic nature of the vowel itself. In clear speech, you tend to pronounce all the plosive bursts at the ends of words. Like you'll say things like cat or dog and things like that. In conversational speech, you tend to omit the plosive bursts at the ends of words. Another thing you don't do in clear speech is you don't do something called degemination. Degemination is a fancy term that says that you take the end of a particular word and merge it into the beginning of the next word. So that happens much less frequently in clear speech. Alveolar flapping happens much less in clear speech than conversational speech. Alveolar flapping is what you do in a word like butter, B-U-T-T-E-R. If you're pronouncing it very formally, you'll say butter. If you're pronouncing it very colloquially or conversationally, you'll say burr, and that's called a flap. And in general, you just delete. MSD stands for miscellaneous sound deletions. In general, you just delete fewer sounds in clear speech and conversational speech. Now, another thing you do when you speak clearly is you change the entire vowel space that you use when you're speaking. And what these are pictures of vowel spaces. I'm not going to go into what they are. The most important thing is to just note that for clear speech, which is the dashed lines here, the vowel spaces are much bigger than that for conversational speech in the solid lines. You can see it in this chart here. Last of all, you change the fundamental spectra of the sounds you say. So what we have here are a bunch of T bursts, at the end in the word cat, for example, averaged over lots of occurrences of T. For conversational, which is the smooth curve, and the dashed curve on top is for clear speech. So you can see that the fundamental spectrum of the sounds actually change when you speak more clearly than when you speak more conversationally. So the bottom line is that we see significant acoustic changes when you speak conversationally, and this impacts both human and machine recognition performance. Okay? Now, in terms of machine recognition performance, we see exactly the same phenomena. And what we have here are a bunch of results over time on different speech tasks, going back to the late 1980s all the way to around 2010 or so. And these different color curves basically represent different styles of speech. So on the left, you see red speech in black. Then you see more formal speech, but not completely red speech, which is broadcast news in blue. You see person-to-person conversation. That's the switchboard task in red. And then you see meeting speech, which is the most difficult speech, up there in pink. Okay? So speaking style clearly affects speech recognition performance. And in order of difficulty, we have red speech, formal speech, person-to-person speech, and then many-person speech. And by the way, to just throw in something parenthetically, when you speak to your favorite voice-activated device, in spite of you may be speaking conversationally to it, you're not. You're actually speaking clearly to this thing. You are doing your best in general to be understood when you talk to a device. So the nature of the speech is inherently much more similar to red speech than meeting room speech. So when you think the speech recognition problem has been solved, if you talk to your device like Google Voice or to Siri or something, keep in mind you are speaking very formally to that device. If you speak much more colloquially, like when you do in meetings, the speech recognition error rates go up dramatically, as shown in these numbers over here, which is speech recognition on meeting speech. And again, these numbers show, what do we have? We have a GMM system, 2 different flavors of deep neural nets. And again, meeting speech is, first of all, difficult, even with recent advances in deep learning. And unlike the switchboard task, there are no human benchmarks I've seen anybody come up with, so we don't even know what is realistic to shoot for here. Okay? Now, another thing that affects speech recognition performance is accents. And first of all, I wanted to say a little bit about the little we know about human intelligibility of accented speech. There are not a lot of studies about this stuff. One study I came across, I thought it was sort of neat, so I wanted to describe it briefly. We have 3 groups of listeners who are exposed to speech with a Slovakian accent. And the claim is that none of these listeners ever heard speech spoken with a Slovakian accent. And the 3 groups break down as follows. The group on the left said they really had no typical experience, no typical exposure to speech with foreign accents. The group on the right said they heard foreign accents all the time, and the group in the middle said they heard a foreign accent at home, none of which, by the way, was Slovakian, but they didn't hear any other foreign accents. And what you see here is that people who have had a lot of exposure to multiple foreign accents, even if those accents are not Slovakian, they tend to do much better than people who have never had any exposure to a foreign accent, and even exposure to one foreign accent over an extended period of time helps you understand speech from a different foreign accent. And this has some obvious implications for what you have to do to build a speech recognition system to get robustness with accent performance. Okay? So in terms of speech recognition performance, here's an interesting study that was done recently by our colleagues at Google. And what they did was they took a system that had been trained on American English. They got some number for speech recognition performance for Indian accents, which was 15%. And when they then train it on Indian accented data, the results improve. No surprise, it moves down from 15% to 11%. Now, what was very interesting about this study is they compared training a set of standard phonetic pronunciation models where you represent each word as a sequence of target pronunciations to a set in which, instead of using the underlying pronunciations, you just model the letter spellings directly. And when you just model the letter spellings directly, at least for people with Indian accents, you get a lot better performance, which is sort of cute and makes sense intuitively, because many foreign speakers of English don't pronounce the word the way they're supposed to be pronounced. They pronounce the word in which the way the word is spelled. And that's why you see this improvement in performance over here. Now, unfortunately, this is not something you can try at home. Okay? These experiments were done on massive amounts of data, 3,000 hours per accent. And another side comment is that these grapheme effects on the letter spellings may be something that's unique to English, which is has notorious problems in the way you pronounce words. The letter spellings have very little often to do with the pronunciations. Okay, next part of the talk is domain robustness. Systems today are now trained on thousands of hours of speech and billions of words of text. Humans recognize a large variety of context by the time they're 20. So you can sort of ask the question, how much speech does a person typically hear by the time you're 20? We go to the source of all human knowledge, which is Yahoo Answers. And Yahoo Answers tells us that a human usually hears about 50,000 words a day, and you speak about 25,000 words a day, depending upon how talkative you are. So that means by the time you're 20, you've heard about 365 million words, give or take a factor of 4. At about 2.5 words a second, this is about 25,000 hours of speech. In terms of how many words do you actually read by the time you're 20, another source of all human knowledge is TechCrunch. And TechCrunch says that at least Americans, pardon the ethnocentricity of the talk, I apologize, consume about 100,000 words per day on the average. That includes all words read, all words heard, etc. And this boils down again to about 365 million words in 20 years. So when you think about it, it's not unreasonable to be training systems on at least 10,000 hours of speech, but it implies that more like 400 million of words of exposure may be enough to understand all domains. So why today are people building systems with billions and hundreds of billions of words of text? Is this really, really necessary? And maybe the answer is no, if you pick the right set of words. So here's a little experiment we did internally. We took a little speech recognition system we had, which is called Baseline, and it had never been exposed to data, to speech from a healthcare domain. It was never exposed to insurance. It was never exposed to something called hospitality, which you could read as sort of a travel domain. And the baseline performance, it's a bunch of numbers, doesn't matter what they are. The important thing to do is to compare the baseline performance to what happens when we adapt the language model on the word transcripts corresponding to just this amount of speech. So with just half an hour of speech, for example, adapting the language model alone knocks the performance down from 31% to 12.8%. For the other two tasks, the effects are not as extreme, but the point is with a relatively little amount of text, you could get a big bang for the buck in terms of performance improvements. And what that's telling us is that not that much data is really needed per domain on top of a good speech recognition base. Now, it's unclear how you really take advantage of this in practice, right? It's unclear how many domains can simply be interpolated together statically. Do we need more work on dynamic adaptation methods? There have been various attempts in the past to do this, but on much older technology bases, and they didn't see great improvements then. But now that we're in the 5 or 6% word error rate range on some tasks, all of a sudden, the effect of the language model becomes much more important, and what didn't work before may work now. Okay, the part that you've all been waiting for, the last part of the talk, okay? And what we'll talk about is learning new languages. So I came across this quote on the internet. If, for the sake of argument, we consider fluency to be the same as being an expert in speaking a language, then a learner may well invest 10,000 hours in language studies to attain fluency. Okay? So it takes thousands of hours of exposure to learn a second language. There were some studies that anecdotally report that third language learning may be somewhat faster with even more ease when you have more languages. So a person who knows 5 languages may learn a 6th language much faster than learning their second language, whatever that means. Very little quantification of this exists, especially for 3 or more languages. This, again, is just a cartoon of time, training time, learning time, versus performance, with one curve representing your second language, the next representing your third language. But the bottom line is that humans do leverage knowledge from other languages to learn new languages, and can machines do the same thing? And what we actually did is we looked at this problem in something called the Babel program, which focused on very rapid learning of speech recognition systems from very little amounts of data, but lots of languages. We actually looked at 28 different languages in this program. And the way we built a system that learns from new languages works as follows. What you do is you take a neural network, which is these light blue things here. This is just a bunch of layers here. And then you train it on a bunch of languages, which are these multicolored things here. And the outputs, the phonetic outputs, there's one set of phonetic outputs for each different language. So the phonetic outputs are different, the input features are different per language, but the network parameters are shared. And you notice this network has a very specific structure. It has this very narrow section here that's referred to as a bottleneck layer. So if you get a new language in, what you could do is you could take this new language, shovel it through this network, and yank out this bottleneck, the activations associated with this bottleneck layer. You don't have to train the network, you just feed it forward through, and pull out this thing which we're going to call a multilingual representation, and treat it as a feature vector. Because for each input feature vector, you get a set of activations we're calling multilingual activations. And this multilingual representation could then be used to train a second network for that target language alone. Another thing you can actually do is you can fine-tune the multilingual representation itself on the language in question. And when you do this, you get improvements in speech recognition performance. So the baseline speech recognition performance, the language here is Javanese. We had 41 hours of training data for Javanese. Word error rate was 62%. When we train it on this multilingual representation on 11 languages, the word error rate goes down to 59%. 28 languages goes down to 56%. And with this fine-tuning, it goes down to 55%. So more languages clearly seem to help performance here. What's less clear is what happens when we build systems with much more data per language. So, in summary, with a lot of domain-specific data, we now can build systems that rival human performance in that domain. And this is driven by advances in deep learning. Noise and reverberation robustness seem to have made serious strides as well in terms of being comparable to humans, and techniques include multi-style training and multi-microphone processing. In other areas, humans still seem to be much more capable. We adapt quickly to accents, we're more flexible in handling a wide variety of domains, and we learn languages robustly with considerably less data. Extremely informal speech, such as what we see in meetings, is still very challenging, and this is no surprise given the extent to which the acoustic properties of the speech change. So the conclusion here is there's still lots of things for speech recognition researchers to work on. I hope some of you pick up this challenge. Teşekkür ederim. Thank you very much. And I don't know if we have any time for questions, Murat. It's running, sort of on time, but...
We're already over time, actually, but maybe 5 minutes, a couple of questions.
The disadvantage of coming before the coffee break, right?
Thank you for the nice presentation. I may have missed a point. I'm sorry if that's the case. My question is whether we can train our model further in unsupervised manner. For example, using some natural language processing tools which check the grammar of a sentence.
Well, you certainly can train a system without without having to have properly transcribed text. You do need to start with a reasonable system, but the problem with unsupervised training is that, at least in our experiments, when we use unlabeled data to train the system, we never get to the same levels of performance as we do with completely properly labeled data. And the issue with grammars used to try and improve, let's say, the transcript of a sentence is that many times people don't speak grammatically. So you could wind up correcting a sentence said ungrammatically into something that's grammatical, but still doesn't match the underlying acoustics. So you have to apply such sorts of techniques very carefully in order to not cause more damage than you already have created.
I see. Thank you. And can lip reading help when available?
Can we say again?
Lip reading.
Lip reading is something that's also used in speech recognition. Actually, at IBM, we had an effort on this many years ago where we were focusing the camera on the face and used it to combine that, to improve the intelligibility of speech and noise. And with the advent of deep neural networks recently, all of a sudden these types of lip reading systems become much, much better. So the answer is yes, but of course you don't always get a chance to get a good high-resolution image of the face when you talk. So the systems I know about that work well typically require fairly high resolution. So if you're very far away from the speaker, you may have trouble leveraging it, but it's a very legitimate way of improving speech recognition performance and noise. And certainly people leverage lip reading cues as well when you're in a noisy environment. So absolutely.
Thank you very much. Thank you very much.